Right now, in laboratories across the world, quantum physicists are conducting experiments that should be impossible. They're watching particles exist in multiple places simultaneously, communicating instantly across vast distances and behaving differently simply because someone is observing them. We thought reality followed logical rules. We were completely wrong. The quantum world operates by principles so bizarre that even Albert Einstein, who helped discover many of them, spent the last decades of his life trying to prove they couldn't be true. He called quantum entanglement spooky action at a distance and insisted that God does not play dice with the universe. But every experiment since has confirmed what Einstein feared most. Reality, at its fundamental level, is stranger than our wildest nightmares. Consider this. Physicists have now measured particles that exist in what they call superposition, literally being in multiple states at once until the moment someone observes them. They've documented pairs of particles that remain mysteriously connected even when separated by millions of miles, influencing each other instantaneously in ways that seem to violate the speed of light. Most disturbing of all, they've discovered that the very act of measurement appears to change reality itself, suggesting that consciousness might play a fundamental role in determining what exists. These discoveries have created what scientists call the measurement problem, a paradox so profound that it challenges our most basic assumptions about existence, causality, and the nature of reality itself. Nobel Prize-winning physicist Eugene Wigner once described it as the point where physics meets the deepest questions of philosophy and human consciousness. Today, nearly a century after quantum mechanics was first formulated, this paradox continues to horrify scientists because its implications are simply too strange to accept, yet too well documented to deny. The numbers are staggering. Quantum tunneling, where particles pass through barriers they shouldn't be able to cross, has been measured with 99.9999% accuracy. Quantum entanglement has been confirmed over distances exceeding 1,400 kilometers in controlled experiments. The delayed choice quantum eraser experiment suggests that decisions made in the present can retroactively determine what happened in the past. These aren't theoretical curiosities. They're the foundations of technologies you use every day. From the processors in your smartphone to the GPS satellites guiding your car. But here's what makes this truly disturbing. The more precisely we measure quantum systems, the more we discover that our fundamental assumptions about reality might be illusions. The idea that objects have definite properties independent of observation, something so basic we never question it, appears to be false at the quantum level. The notion that cause precedes effect, that information cannot travel faster than light, that particles exist in specific locations. All of these common sense principles break down in the quantum realm. Leading quantum physicists like David Bohm, Hugh Everett, and John Bell have proposed interpretations of these phenomena that range from multiple parallel universes to consciousness, creating reality to hidden variables that connect everything in ways we can't detect. Each interpretation solves some aspects of the quantum paradox while creating new ones that are equally disturbing. The most widely accepted interpretation, developed by Niels Bohr and Werner Heisenberg, essentially argues that quantum systems don't have definite properties at all until they're measured, a conclusion so radical that it suggests reality as we experience it might be fundamentally different from reality as it actually exists. What makes this particularly unsettling is that quantum effects aren't confined to the microscopic world. Researchers have now demonstrated quantum superposition in increasingly large objects, from individual atoms to molecules containing thousands of atoms. Some scientists believe that quantum effects might play a role in biological processes like photosynthesis, bird navigation, and possibly even consciousness itself. The boundary between the quantum world and our everyday experience isn't as clear as we once believed. Tonight, we're going to explore the quantum paradoxes that continue to baffle and horrify scientists. We'll discover how particles can be in multiple places at once, how measuring one particle can instantly affect another across the universe, and how the very act of observation seems to create the reality we experience. We'll examine experiments that suggest the past might not be fixed until we observe it in the present. And we'll confront the possibility that consciousness itself might be woven into the fabric of reality in ways that challenge everything we thought we knew about existence. But most importantly, we'll grapple with the profound implications of these discoveries. If quantum mechanics is correct, and every experiment suggests it is, then the universe is far stranger, more mysterious, and more deeply interconnected than we ever imagined. The paradoxes we'll explore don't just challenge our understanding of physics. They force us to reconsider the nature of reality itself, the role of consciousness in the universe, and what it means to exist in a cosmos where observation creates experience and where the boundaries between observer and observed might be fundamental illusions. If you're ready to have your understanding of reality fundamentally challenged, subscribe and hit that thumbs up button. And here's a question that will haunt you by the end of this video. If consciousness is required to collapse quantum superpositions, and if consciousness itself emerges from quantum processes in the brain, who or what is observing the universe into existence? Comment below with your thoughts. I'll pin the most mind-bending response as we journey into the quantum realm. Remember that we're not just exploring abstract physics. We're investigating the very foundations of existence itself. The quantum world reveals that reality might be far more malleable, mysterious, and consciousness-dependent than we ever dreamed. Every paradox we encounter will peel back another layer of what we thought we knew about the nature of existence. Now let's begin by discovering how particles learn to exist in multiple places at once, and why this simple fact has been keeping physicists awake at night for nearly a century. Chapter 1. Quantum Existence. The horror began in 1909 when physicist Jeffrey Taylor conducted what should have been a simple experiment. He wanted to understand the nature of light by sending photons one at a time through two parallel slits and observing where they landed on a screen behind them. Logic dictated that each photon, being a single particle of light, would pass through one slit or the other and create two distinct lines on the screen corresponding to each opening. Instead, Taylor observed something that violated every principle of classical physics. The photons, even when sent individually with minutes between each one, somehow created an interference pattern, alternating bands of light and dark that could only result if each photon had passed through both slits simultaneously and interfered with itself. This was impossible. A single particle cannot be in two places at once. Yet there it was, documented with scientific precision that would be replicated thousands of times over the following century. What Taylor had discovered was quantum superposition, the principle that particles exist in multiple states simultaneously until they're observed or measured. In the quantum realm, a photon doesn't choose between passing through the left slit or the right slit. It passes through both, existing in what physicists call a superposition state that encompasses all possibilities at once. Only when we try to detect which slit it passes through does the photon collapse into a definite state, choosing one path or the other. This discovery sent shockwaves through the scientific community because it challenged the fundamental assumption that objects have definite properties, independent of observation. In our everyday experience, a baseball thrown through the air has a specific location, velocity, and trajectory at every moment. We might not know these properties precisely, but we assume they exist whether we measure them or not. Quantum mechanics suggests this assumption is wrong at the most basic level of reality. The mathematics of quantum superposition, developed by Erwin Schrödinger and Werner Heisenberg in the 1920s, describes particles not as objects with definite properties, but as probability waves, mathematical expressions that represent all possible states the particle could be in. These probability waves evolve according to precise equations that predict the likelihood of finding the particle in any particular state when measured. But they say nothing about what state the particle is actually in before measurement. To understand how profoundly this challenges our intuition, consider what happens when we scale up quantum superposition. In 1935, Schrödinger illustrated the paradox with his famous thought experiment involving a cat placed in a sealed box with a quantum-triggered poison mechanism. According to quantum mechanics, before opening the box to observe the cat, the quantum trigger exists in superposition, both triggered and not triggered simultaneously. This means the cat should also exist in superposition, being both alive and dead until observed. Schrödinger intended this as a reduction to absurdity, showing that quantum mechanics couldn't possibly apply to large objects. But subsequent experiments have demonstrated quantum superposition in increasingly large systems. In 2019, researchers at the University of Vienna achieved superposition in molecules containing over 2,000 atoms. Other experiments have demonstrated superposition effects in superconducting circuits large enough to see with the naked eye. The boundary between the quantum world and our everyday experience keeps expanding, making Schrodinger's cat less absurd and more prophetic. The implications become even more disturbing when we consider what this means for human consciousness. Your brain contains roughly 86 billion neurons, each connected to thousands of others through synapses that rely on electrochemical processes. Many of these processes operate at scales where quantum effects become significant. Some researchers, including Nobel Prize winner Roger Penrose, have proposed that consciousness itself might emerge from quantum processes in brain microtubules, suggesting that our awareness could be fundamentally quantum in nature. If consciousness is quantum, then the observer paradox becomes even more profound. We assume that we observe reality as conscious beings. But if consciousness itself is created through quantum processes, then what determines the specific quantum state that gives rise to our particular conscious experience? This creates what philosophers call the hard problem of consciousness, explaining how subjective awareness emerges from objective physical processes. Recent experiments have pushed the boundaries of quantum superposition even further. The delayed choice quantum eraser experiment, first proposed by John Wheeler and successfully conducted by multiple research teams, demonstrates that particles can exist in superposition not just across space, but across time. In these experiments, the decision of whether to measure a particle's path can be made after the particle has already passed through the apparatus. Yet this future decision retroactively determines whether the particle was in superposition or had a definite path. This temporal aspect of quantum superposition suggests that the past might not be as fixed as we assume. If future measurements can retroactively determine past states, then causality itself becomes questionable in the quantum realm. Events that we think of as sequential, cause followed by effect, might be more interconnected and temporally flexible than our everyday experience. Suggests the horror that physicists feel when contemplating quantum superposition isn't just academic. These principles form the foundation of emerging technologies that will reshape civilization. Quantum computers exploit superposition to process information in ways that classical computers cannot, potentially solving problems that would take conventional computers millions of years. Quantum cryptography uses superposition to create communication systems that are theoretically unbreakable, because any attempt to eavesdrop would destroy the quantum states carrying the information. But perhaps most unsettling is the realization that quantum superposition might be happening constantly around us, invisible only because we're too large and our environment too noisy to maintain the delicate conditions required for quantum coherence. Every interaction with the environment, every collision with an air molecule, every photon of light causes quantum decoherence, forcing superposed states to collapse into definite realities. This suggests that the classical world we experience might be an emergent property of countless quantum systems interacting with their environment, constantly collapsing superpositions into the definite states we perceive as reality. We're not separate from quantum mechanics. We're swimming in an ocean of quantum processes, but our consciousness aggregates into the coherent experience we call existence. The mathematics of superposition reveals something even more profound. The act of measurement doesn't just reveal pre-existing properties. It actively participates in creating the reality being measured. When we observe a quantum system, we become entangled with it, and the boundary between observer and observed becomes fundamentally blurred. This participatory universe, where consciousness and reality co-create each other, represents a radical departure from the objective materialism that has dominated Western science for centuries. As we stand on the threshold of deeper quantum mysteries. Consider this: every atom in your body, every photon hitting your retina as you read these words, every electrical signal in your nervous system operates according to quantum principles. The superposition states that horrify physicists aren't abstract concepts happening in distant laboratories. They're the invisible foundation of your existence, constantly collapsing and reforming to create the continuous stream of experience you call consciousness. But superposition is only the beginning of quantum strangeness. The real horror begins when we discover that particles separated by vast distances can remain mysteriously connected, influencing each other instantaneously in ways that seem to mock our understanding of space, time, and causality. Chapter 2. Spooky Connections. In 1935, three physicists published a paper that was meant to destroy quantum mechanics forever. Albert Einstein, Boris Podolsky, and Nathan Rosen crafted what they believed was the perfect argument against the bizarre implications of quantum theory. They described a thought experiment involving two particles that had interacted and then been separated by enormous distances. According to quantum mechanics, measuring one particle would instantly determine the state of the other, regardless of how far apart they were. Einstein and his colleagues argued this was impossible because it would require information to travel faster than light, violating special relativity. They concluded that quantum mechanics must be incomplete. There had to be hidden variables that predetermined the particle's properties, creating only the illusion of instantaneous connection. Einstein famously declared that God does not play dice with the universe, and dismissed quantum entanglement as spooky action at a distance. Einstein was wrong, and the discovery of just how wrong he was has become one of the most horrifying revelations in the history of science. In 1964, physicist John Bell proved mathematically that no theory based on local hidden variables could reproduce the predictions of quantum mechanics. Bell's theorem showed that any realistic explanation of quantum entanglement would have to abandon either locality, the idea that objects are only influenced by their immediate surroundings, or realism, the idea that objects have definite properties, independent of measurement. The universe could not be both local and realistic if quantum mechanics was correct. The first definitive test of Bell's theorem came in 1981 when Alain Aspect and his team at the University of Paris conducted experiments with entangled photons. They measured the polarizations of photon pairs that had been separated by distances that made any communication between them impossible, even at light speed. The results violated Bell's inequality by a wide margin, confirming that quantum entanglement was real and that Einstein's spooky action at a distance was an accurate description of how the universe actually works. The implications were staggering. Two particles that had once interacted remained connected in a way that transcended space and time. Measuring the spin of one particle along any axis would instantly determine the spin of its entangled partner along the same axis, even if they were separated by millions of miles. This correlation wasn't explained by any signal passing between the particles. It was instantaneous, complete, and seemingly magical. But the horror of quantum entanglement goes far deeper than simple instantaneous correlation. When we measure one particle of an entangled pair, we don't just learn about its state. We actively determine the state of both particles simultaneously. Before measurement, both particles exist in superposition, with neither having definite properties. The act of measurement on one particle forces both particles to choose corresponding states, collapsing the quantum superposition of the entire entangled system. This means that entangled particles aren't separate objects that happen to be correlated. They're part of a single quantum system that maintains its unity regardless of spatial separation. Distance becomes irrelevant at the quantum level. The entangled particles behave as one object distributed across space, responding to measurement as a unified whole rather than as separate entities. Recent experiments have pushed quantum entanglement to extraordinary scales. In 2017, Chinese scientists successfully demonstrated quantum entanglement between a satellite in orbit and ground stations, separated by over 1,400 kilometers. In 2019, researchers achieved entanglement between quantum processors in separate buildings, creating what they called a quantum internet connection. These experiments prove that entanglement isn't limited to microscopic particles in carefully controlled laboratory conditions. It's a fundamental feature of reality that operates across any distance. The temporal aspects of entanglement are even more disturbing. Experiments in quantum teleportation have shown that the quantum state of one particle can be transferred to another particle instantly, regardless of the distance between them. The original particle's state is destroyed in the process, but its quantum information reappears in the distant particle faster than light could travel between them. This isn't science fiction. It's documented science that challenges our basic understanding of information, identity, and causality. But perhaps the most unsettling aspect of quantum entanglement is its universality. Every particle in the universe has interacted with other particles throughout cosmic history, creating a vast web of entangled connections. The photons hitting your eyes right now were once entangled with particles in the stars that created them. The atoms in your body were forged in ancient supernovas and remain quantum mechanically connected to particles scattered across the cosmos. This suggests that the universe isn't composed of separate objects interacting across empty space. Instead, it appears to be a single, unified quantum system where the appearance of separation is an emergent property of how we observe reality. John Wheeler, one of the pioneers of quantum mechanics, described this as a participatory universe where observation and reality are fundamentally intertwined. The philosophical implications are profound. If entanglement reveals the fundamental interconnectedness of all things, then the boundaries we perceive between self and world, observer and observed, might be artificial constructions rather than fundamental features of reality. The mystics and philosophers who have long argued for the underlying unity of existence find unexpected support in quantum mechanics. This interconnectedness becomes even more mysterious when we consider consciousness itself. If your brain operates through quantum processes, and if consciousness emerges from the complex interactions of quantum systems, then your awareness might be entangled with the quantum processes occurring throughout the universe. Some physicists have proposed that consciousness itself might be a quantum phenomenon that connects observers across space and time. The horror that scientists feel when confronting entanglement isn't just intellectual, it's existential. The discovery that reality is fundamentally non-local and non-realistic undermines the mechanistic worldview that has dominated science since Newton. Objects don't have independent existence. Properties don't exist before measurement. Cause and effect become blurred when particles can influence each other instantaneously across any distance. Modern quantum technologies exploit entanglement in ways that seemed impossible just decades ago. Quantum computers use entangled qubits to process information exponentially faster than classical computers. Quantum cryptography creates communication channels that are fundamentally secure because any attempt to eavesdrop breaks the entanglement and reveals the intrusion. Quantum sensors can detect changes so minute that they approach the theoretical limits imposed by the uncertainty principle itself, but these practical applications pale beside the conceptual revolution that entanglement represents. If particles separated by billions of light years remain connected through quantum entanglement, then the universe is far more unified and mysterious than our everyday experience suggests. The boundaries between here and there, now and then, self and other, might be conceptual conveniences rather than fundamental features of reality. Recent theoretical work in quantum gravity suggests that entanglement might be even more fundamental than space and time themselves. Some physicists propose that space-time emerges from more basic quantum entanglements, meaning that the fabric of reality is woven from the invisible connections between quantum systems. In this view, entanglement doesn't just occur within space and time. It creates space and time. This brings us to what many consider the most disturbing aspect of quantum entanglement: its implications for free will and determinism. If your consciousness is quantum mechanical, and if quantum systems are fundamentally entangled with the broader universe, then your thoughts and decisions might be influenced by quantum connections that extend far beyond your local brain. The feeling of making independent choices might be an illusion created by your limited perspective on a vast, interconnected quantum system. As we contemplate the reality of quantum entanglement, we must confront the possibility that separation is the ultimate illusion. The particles that make up your body, the photons carrying these words to your consciousness, the neurons firing as you process these ideas, all of them remain quantum, mechanically connected to the broader cosmos in ways that transcend our ordinary understanding of space, time, and identity. But entanglement is only one aspect of quantum horror. Even more disturbing is the discovery that the very act of measurement appears to change reality itself, suggesting that consciousness might play a fundamental role in determining what exists. Chapter 3. Observer Horror. The most terrifying experiment in physics was first conducted in 1909. Replicated thousands of times since, and still defies every attempt at common-sense explanation. It's called the double-slit experiment, and it reveals that the universe behaves fundamentally differently when no one is watching. When we fire electrons one at a time toward a barrier with two parallel slits, something impossible happens. Each electron, despite being a single particle, somehow passes through both slits simultaneously and interferes with itself on the detection screen, creating the characteristic wave pattern of alternating bright and dark bands. This is quantum superposition in action. The electron exists in multiple states until it's detected. But here's where the horror begins. The moment we place a detector at either slit to determine which path the electron takes, the wave pattern disappears. The electron suddenly behaves like a classical particle, passing through only one slit and creating two distinct bands on the screen instead of the interference pattern. The detector doesn't physically interact with the electron in any meaningful way. It simply observes it. Yet, this act of observation fundamentally changes the electron's behavior. This phenomenon, known as the measurement problem, suggests that reality itself depends on whether someone is watching. The electron doesn't have a definite path until we observe it. Our observation doesn't just reveal pre-existing properties. It actively creates the reality being observed. This violates our most basic assumptions about the independence of objective reality from conscious observation. The implications become even more disturbing when we consider what constitutes measurement or observation in quantum mechanics. It's not that human consciousness is required any interaction that extracts information about a quantum system can cause wave function collapse. A particle detector, a computer recording data, even a single atom interacting with the quantum system can serve as an observer that collapses superposition into definite states. But this raises an even deeper question. If any interaction can cause wave function collapse, how do quantum systems maintain coherence long enough to display quantum effects? The answer reveals another layer of quantum horror, the concept of quantum decoherence. Quantum systems exist in superposition only when they're isolated from their environment. Any interaction with the surrounding world, collision with an air molecule, absorption of a random photon, thermal vibration can cause decoherence, collapsing the superposition into a definite classical state. In our everyday world, objects are constantly interacting with their environment, making quantum superposition effectively impossible to maintain, except under the most carefully controlled laboratory conditions. This means that the classical reality we experience emerges from the constant collapse of quantum superpositions through environmental decoherence. We're not separate from quantum mechanics, we're immersed in it. The solid, definite world we perceive is actually a statistical average of countless quantum interactions, each one collapsing superpositions and creating the appearance of classical behavior. But the measurement problem goes deeper than simple wave function collapse. In 1961, physicist Eugene Wigner proposed a thought experiment that pushed the observer paradox to its logical extreme. Wigner imagined his friend conducting a quantum measurement in an isolated laboratory. From Wigner's perspective outside the lab, his friend and the quantum system should both be in superposition until Wigner opens the lab door and observes the result. This creates what's known as Wigner's friend paradox. When exactly does wave function collapse occur? When Wigner's friend makes the measurement or when Wigner observes his friend? If consciousness is required for wave function collapse, whose consciousness counts? The paradox suggests that either quantum mechanics is incomplete, or consciousness plays a more fundamental role in physical reality than we've ever imagined. Some interpretations of quantum mechanics take this implication seriously. The consciousness-based interpretation, associated with physicists like John von Neumann and Henry Stapp, proposes that consciousness is what causes wave function collapse. In this view, the universe exists in quantum superposition until conscious observers collapse it into definite states through the act of measurement. This interpretation is deeply troubling because it suggests that consciousness isn't just an emergent property of complex physical systems. It's a fundamental feature of reality that actively participates in creating the world we experience. If true, this would mean that the universe looked very different before conscious beings evolved to observe it. existing in vast quantum superpositions that were never collapsed into definite states. Other interpretations try to avoid the consciousness problem, but create their own disturbing implications. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that wave function collapse never actually occurs. Instead, every quantum measurement splits the universe into multiple parallel realities, each containing a different outcome. In this view, every time you observe a quantum system, you create countless alternative versions of yourself, experiencing different results. According to many worlds, there are versions of you right now reading these words where every quantum measurement in your brain's neurons produce different outcomes, creating slightly different thoughts and experiences. The number of parallel universes created by quantum measurements is staggering. Some estimates suggest that every quantum interaction creates billions of new universes every second. The de Broglie bomb interpretation takes a different approach, proposing that particles have definite positions and velocities at all times, guided by a quantum potential that creates the illusion of wave-particle duality. This preserves realism and determinism, but requires accepting that the quantum potential carries information instantaneously across any distance, making the universe fundamentally non-local. Each interpretation of quantum mechanics solves some aspects of the measurement problem while creating new paradoxes that are equally disturbing. The fact that nearly a century after quantum mechanics was formulated, physicists still can't agree on what it means reveals just how profound the observer paradox really is. Recent experiments have made the measurement problem even more acute. Quantum delayed choice experiments show that the decision to measure a particle's wave or particle properties can be made after the particle has already interacted with the experimental apparatus. Yet this future decision retroactively determines how the particle behaved in the past. This suggests that the flow of causality itself might be different in the quantum realm. The quantum Zeno effect demonstrates another aspect of observer horror. By measuring a quantum system repeatedly, observers can actually prevent it from evolving, freezing it in its initial state through the act of observation. This shows that observation doesn't just reveal reality, it can actively control the evolution of quantum systems. But perhaps the most disturbing aspect of the measurement problem is its implications for the nature of time itself. If wave function collapse creates definite states from quantum superpositions, and if this process is fundamentally random as quantum mechanics suggests, then the future emerges from genuine quantum randomness rather than deterministic causation. The universe doesn't follow a predetermined script. It improvises its way into existence through countless quantum measurements. This quantum randomness isn't just uncertainty about outcomes that are already determined. It's genuine indeterminacy. The universe literally doesn't know what will happen until quantum measurements force definite outcomes. This makes the future genuinely open and suggests that determinism, like classical objectivity, might be an emergent illusion rather than a fundamental feature of reality. The measurement problem also raises questions about the nature of information itself. Quantum mechanics suggests that information is more fundamental than matter or energy. Quantum states are essentially informational rather than material. When we measure a quantum system, we're not just observing physical properties. We're extracting information from the quantum field that underlies physical reality. This informational view of quantum mechanics has led some physicists to propose that consciousness itself might be an informational phenomenon that emerges from quantum processes. If consciousness is how the universe processes information about itself, then the measurement problem becomes a question about how reality becomes self-aware through conscious observation. as we grapple with the implications of quantum measurement. We must confront the possibility that observation and reality are far more intertwined than we ever imagined. The universe might not be a collection of objects that exist independently of observers. Instead, it might be an ongoing conversation between consciousness and quantum fields, with measurement serving as the medium through which potential becomes actual and possibility becomes experience. But the observer paradox is only one facet of quantum horror. Even more disturbing is the discovery that individual quantum systems can exist in multiple contradictory states simultaneously, defying logic itself and forcing us to reconsider the nature of existence. Chapter 4. Logic's Collapse in 1935. Erwin Schrödinger proposed a thought experiment that was meant to expose the absurdity of quantum mechanics. He described a cat placed in a sealed box with a Geiger counter connected to a hammer that would break a flask of poison if it detected radiation from a radioactive atom. According to quantum mechanics, before opening the box, the radioactive atom exists in superposition, both decayed and not decayed simultaneously. This should mean the cat is also in superposition, both alive and dead until observed. Schrödinger intended this as a reductio ad absurdum, showing that quantum mechanics couldn't possibly apply to macroscopic objects. Instead, he accidentally created the most famous illustration of quantum mechanics' assault on classical logic. The cat paradox reveals that at the quantum level, the fundamental principle of non-contradiction, that something cannot both be and not be at the same time, simply doesn't apply. The horror of Schrödinger's cat isn't just theoretical anymore. In recent decades, physicists have created increasingly large quantum superposition states that push the boundaries of what we thought possible. In 1996, researchers achieved superposition in a single atom. By 2013, they had extended superposition to molecules containing over 400 atoms. In 2019, scientists demonstrated quantum superposition in molecules containing more than 2,000 atoms, each molecule existing in multiple positions simultaneously. These experiments reveal that the boundary between the quantum world and our everyday experience isn't as clear as we once believed. The principles that govern the microscopic realm, including the violation of classical logic, extend further into the macroscopic world than anyone imagined. We're not separate from quantum weirdness. We're surrounded by it, immersed in it, and quite possibly composed of it. But the collapse of classical logic in quantum mechanics goes far beyond simple superposition. Consider the phenomenon of quantum tunneling, where particles pass through barriers they don't have enough energy to surmount. Classical logic says this is impossible. An object cannot be on both sides of an impenetrable barrier simultaneously. Yet quantum tunneling is so common and well documented that it's the basis for technologies you use every day, from the flash memory in your smartphone to the scanning tunneling microscopes that image individual atoms. In quantum tunneling, a particle doesn't go around or over a barrier. It genuinely exists on both sides of the barrier, simultaneously until measurement collapses the superposition. The particle has a definite probability of being found on either side, but no definite location until observed. This violates the classical principle that objects have continuous trajectories through space and time. Even more disturbing is the concept of quantum indeterminacy, which suggests that certain properties of quantum systems literally don't exist until they're measured. This isn't hidden variable theory, where properties exist but are unknown to us. Quantum mechanics asserts that properties, like a particle's exact position or momentum, genuinely don't have definite values until measurement forces them to choose specific states. This challenges the law of the excluded middle, the logical principle that every proposition is either true or false. In quantum mechanics, propositions about unmeasured properties of quantum systems are neither true nor false. They're indeterminate. A particle's spin isn't up or down until measured. It exists in a quantum superposition that transcends classical true-false logic. The violation of classical logic becomes even more pronounced when we consider quantum entanglement between multiple particles. Einstein, Podolsky, and Rosen argued that if quantum mechanics were correct, measuring one particle would instantaneously determine the state of distant entangled particles, violating the principle that information cannot travel faster than light. They concluded this reductio ad absurdum proved quantum mechanics was incomplete. But Bell's theorem, confirmed by countless experiments, proves that any complete theory of quantum mechanics must violate either locality, the principle that objects are only influenced by their immediate surroundings, or realism, the principle that objects have definite properties, independent of measurement. The universe cannot be both local and realistic. Classical logic demands that one of these principles must be true, but quantum mechanics forces us to abandon both. This creates what philosophers call quantum logic, a non-classical logical system where the principle of distributivity fails. In classical logic, if A and B or C are true, then A and B or A and C must also be true. But quantum systems can exist in superpositions where this principle breaks down. A particle can have definite energy while existing in a superposition of different positions, violating the classical relationship between joint and separate probability distributions. The collapse of classical logic in quantum mechanics has profound implications for how we understand truth, existence, and reality itself. If the fundamental constituents of reality don't obey classical logic, then logic itself might be an emergent property of large-scale systems rather than a fundamental feature of existence. The principles we use to reason about the world, non-contradiction, excluded middle, distributivity, might be approximations that work well for everyday experience but fail at the quantum level. This suggests that mathematics itself, which underlies all scientific reasoning, might be fundamentally limited in its ability to describe quantum reality. Gödel's incompleteness theorems already showed that mathematical systems cannot prove their own consistency. Quantum mechanics adds another layer of limitation. The logical principles underlying mathematics might not apply to the physical systems mathematics attempts to describe. Recent experiments in quantum foundations have pushed these logical paradoxes to their extremes. The quantum delayed choice eraser experiment demonstrates that particles can exist in superpositions not just of position or momentum, but of their entire causal history. A photon can simultaneously take two different paths through an experimental apparatus, and the decision about which path to measure can be made after the photon has already been detected, retroactively determining which path it actually took. This temporal aspect of quantum superposition violates the classical principle that the past is fixed and determinate. In quantum mechanics, the past can exist in superposition until future measurements collapse it into definite states. This suggests that causality itself might be more flexible and observer-dependent than we assumed. The violation of classical logic also appears in quantum computing, where quantum computers exploit superposition and entanglement to process information in ways that classical computers cannot. A classical bit must be either 0 or 1, following the principle of excluded middle. But a quantum bit, qubit, can exist in superposition, being simultaneously 0 and 1 until measured. This allows quantum computers to explore multiple computational paths simultaneously, solving certain problems exponentially faster than classical computers. But perhaps the most disturbing implication of logic's collapse is what it suggests about consciousness and human reasoning. If the brain operates through quantum processes, and there's growing evidence that it might, then consciousness itself might transcend classical logic. The feeling of having definite thoughts and beliefs might be similar to quantum wave function collapse, where the brain's quantum superpositions collapse into definite conscious states through the act of introspection. This could explain some of the paradoxes of human consciousness, such as the ability to hold contradictory beliefs simultaneously, or the phenomenon of cognitive superposition, where we entertain multiple possibilities before making decisions. If consciousness is quantum mechanical, then the logical principles we use to reason about the world might not apply to reasoning itself. The collapse of logic in quantum mechanics also challenges our understanding of identity and existence. In classical logic, identity is absolute. Something is either identical to itself or it isn't. But quantum particles don't have definite identities until measured. Two particles in an entangled superposition don't have separate, distinguishable identities. They exist as a single quantum system distributed across space. This suggests that individuality itself might be an emergent property rather than a fundamental feature of reality. The boundaries between self and world, between one object and another, might be conceptual constructions that break down at the quantum level. If consciousness is quantum mechanical, then the sense of being a separate, individual self might be similar to wave function collapse, a definite identity emerging from an underlying quantum superposition of possibilities. As we confront the collapse of classical logic in quantum mechanics, we must grapple with the possibility that reason itself is limited in its ability to comprehend reality. The principles we've used to understand the world for thousands of years, non-contradiction, excluded middle, causality, might be cognitive tools that work well for everyday experience, but fail to capture the true nature of existence. The quantum realm doesn't just challenge our knowledge. It challenges the very foundations of how we think. It suggests that reality operates according to principles so foreign to human intuition that our logic breaks down when we try to comprehend them. We're forced to embrace paradox, contradiction, and indeterminacy as fundamental features of existence rather than the signs of incomplete understanding. But the assault on logic is only the beginning. Even more terrifying is the discovery that time itself might not flow as we experience it, and that the future might influence the past in ways that shatter our understanding of causality. Chapter 5. Temporal Madness. In 1978, physicist John Wheeler proposed an experiment so disturbing that it challenged the very foundations of causality. Wheeler's delayed choice experiment suggested that decisions made in the present could retroactively determine what happened in the past, not just our knowledge of past events, but the events themselves. When this experiment was finally conducted in the 1980s and refined in subsequent decades, it confirmed Wheeler's most unsettling predictions and revealed that time itself might not work the way we assume. The experiment begins with the classic double-slit setup, where photons can either behave as waves, passing through both slits and creating interference patterns, or as particles, passing through one slit and creating discrete impact points. In Wheeler's delayed choice version, the decision about whether to measure the photon's wave or particle behavior is made after the photon has already passed through the slits, but before it reaches the detector. According to classical intuition, this delay shouldn't matter. The photon should have already decided whether to behave as a wave or particle when it passed through the slits. But quantum mechanics predicts something impossible. The future measurement decision should retroactively determine the photon's past behavior. If we choose to measure particle behavior, the photon should retroactively become a particle that passed through only one slit. If we choose to measure wave behavior, it should retroactively become a wave that passed through both slits. Every experimental test of Wheeler's delayed choice scenario has confirmed this impossible prediction. The photon's behavior through the slits is indeed determined by a measurement decision made after it has already passed through the apparatus. The future literally influences the past in ways that violate our most basic understanding of causality. But this temporal madness goes far beyond delayed choice experiments. In 2007, researchers extended the delayed choice concept to quantum entanglement in what's called the delayed choice entanglement swapping experiment. In this setup, 4 photons are created in separate locations. 2 of the photons are measured immediately, while the other 2 are subjected to a Bell state measurement that either entangles them or doesn't. Here's where it becomes truly disturbing. The Bell state measurement can be performed after the first 2 photons have already been detected and their correlations recorded. Yet the results show that if the second pair is entangled, the first pair retroactively becomes entangled too, even though they were measured before the entanglement decision was made. The past correlation between the first pair depends on a future measurement of the second pair. This suggests that entanglement itself can exist backward in time. Particles can become quantum mechanically connected not just across space, but across time, with future events determining past relationships. The implications are staggering. If consciousness is quantum mechanical, and if quantum effects can propagate backward in time, then our present thoughts and decisions might influence our past mental states in ways we can't detect. The temporal aspects of quantum mechanics become even more mysterious when we consider the role of information. Quantum mechanics suggests that information is more fundamental than matter or energy. Quantum states are essentially informational structures that determine how particles behave when measured. But if information can flow backward in time through quantum processes, then the future might be constantly influencing the past in ways that preserve consistency while allowing for genuine temporal flexibility. This creates what physicists call the grandfather paradox of quantum mechanics. In classical time travel scenarios, changing the past creates logical contradictions. But quantum mechanics might resolve these paradoxes through superposition and many world splitting. If you could quantum mechanically influence the past, you might create a superposition of different past states rather than changing a single, definite history. Recent theoretical work in quantum gravity suggests that time itself might emerge from quantum entanglement, rather than being a fundamental feature of reality. In this view, the flow of time we experience is a macroscopic approximation of more fundamental quantum processes that connect events across space and time through entanglement. Time doesn't exist independently of matter and consciousness. It's created by the network of quantum relationships between observers and observed systems. This emergent view of time helps explain some of the temporal paradoxes in quantum mechanics. If time emerges from quantum entanglement, then quantum processes that transcend space-time limitations might be able to influence the apparent flow of time itself. Measurement doesn't just reveal properties of quantum systems. It participates in creating the temporal framework within which those properties exist. The implications for consciousness are profound and disturbing. If time is emergent from quantum processes, and if consciousness is quantum mechanical, then conscious awareness might play a role in creating the temporal structure of reality. The flow of time you experience might not be independent of your consciousness. It might be partially created by the quantum processes underlying your awareness. This connects to a disturbing possibility raised by some quantum theorists, that consciousness might be able to influence quantum systems backward in time through what's called retrocausal quantum mechanics. In this interpretation, conscious observers don't just collapse wave functions in the present. They participate in a temporal dialogue with quantum systems that extends into both past and future. Some experiments suggest this might already be happening. Studies of quantum random number generators show subtle correlations with future events that should be impossible if time flows in only one direction. Parapsychology researchers claim to have documented precognitive effects where people respond to future stimuli before those stimuli are presented. While these effects are controversial and difficult to replicate, they hint at the possibility that consciousness might have access to quantum information that transcends normal temporal limitations. The delayed choice quantum eraser experiment pushes temporal madness even further. In this setup, photons pass through a double-slit apparatus and are then directed toward detectors that either preserve or erase information about which slit the photon passed through. The decision to preserve or erase this switch path information can be made after the photon has already been detected at the main screen. The results are impossible according to classical causality. Whether an interference pattern appears on the main screen depends on a future decision about whether to erase the switch path information. If the information is erased, an interference pattern appears retroactively. If the information is preserved, no interference pattern appears. The past measurement result depends on a future measurement decision. This suggests that information itself might be more temporally flexible than we assume. Quantum systems might exist in superpositions, not just of position and momentum, but of their entire causal history. The past doesn't become fixed until all relevant information has been processed by all observers across all times involved in the quantum measurement process. But perhaps the most disturbing aspect of quantum temporal madness is its implications for free will and determinism. If the future can influence the past through quantum processes, then the traditional debate between determinism and free will becomes meaningless. The future isn't determined by the past because the past isn't fixed until the future has been observed. Causality becomes circular, with past and future mutually determining each other through quantum processes. This circular causality might explain some puzzling aspects of consciousness, such as the feeling of making free choices in a physically deterministic universe. If consciousness is quantum mechanical, and if quantum processes can influence their own past states, then conscious decisions might genuinely create the neural conditions that led to those decisions in the first place. Free will becomes a temporal loop where choices create their own causal foundations. The many worlds interpretation adds another layer of temporal complexity. If every quantum measurement splits the universe into multiple parallel realities, then the delayed choice experiments might be selecting which branch of the multiverse becomes real for the observer. The past doesn't change. Instead, the observer's future determines which of many possible paths they experience as their reality. Recent experiments with quantum computers have begun to explore the computational implications of temporal quantum effects. Quantum algorithms that exploit temporal superposition might be able to solve certain problems by processing information that flows backward from future computation states. This could lead to computing paradigms that transcend the linear processing limitations of classical computation. As we grapple with the temporal madness of quantum mechanics, we must confront the possibility that time itself is far stranger and more malleable than we ever imagined. The neat division between past, present, and future that structures human experience might be a cognitive illusion, created by consciousness interacting with quantum fields that transcend temporal limitations. The flow of time might not be a fundamental feature of reality, but an emergent property of how conscious observers navigate quantum superpositions. In this view, the experience of temporal sequence emerges from the collapse of quantum superpositions, rather than existing independently of consciousness. Time doesn't carry consciousness forward. Consciousness creates time through the continuous collapse of quantum possibilities into experienced realities. But temporal paradoxes are only one aspect of quantum horror. Even more unsettling is the growing evidence that consciousness itself might be fundamentally quantum mechanical, suggesting that the boundary between mind and reality is far more blurred than we ever suspected. Chapter 6. Conscious Entanglement. Most disturbing question in science isn't about distant galaxies or subatomic particles. It's about the nature of your own consciousness. As you read these words, roughly 86 billion neurons in your brain are firing in precise patterns, creating the subjective experience you call awareness. But how does objective neural activity give rise to subjective consciousness? And more terrifyingly, what if consciousness isn't just produced by quantum processes, but is itself a fundamental quantum phenomenon? This question became urgent in the 1990s when anesthesiologist Stuart Hameroff and mathematical physicist Roger Penrose proposed that consciousness emerges from quantum processes in microtubules, tiny structures within brain cells. According to their theory, consciousness isn't just an emergent property of neural networks, but a quantum mechanical phenomenon that allows the brain to process information in ways that classical physics cannot explain. The ORC, orchestrated objective reduction theory, suggests that microtubules in neurons can maintain quantum superposition states for brief periods before collapsing into definite configurations that correspond to conscious moments. In this view, consciousness literally emerges from quantum wave function collapse, with each moment of awareness corresponding to a quantum measurement event in the brain's quantum processing system. If this theory is correct, then consciousness isn't separate from the quantum realm. It's quantum mechanics in action. Every thought, every decision, every moment of subjective experience would be the result of quantum superpositions collapsing into definite mental states. The boundary between mind and quantum reality would disappear entirely. Recent experimental evidence has begun to support the quantum consciousness hypothesis. In 2013, researchers at the Max Planck Institute discovered quantum coherence effects in microtubules isolated from brain tissue. In 2014, scientists found evidence of quantum entanglement in bird brains, specifically in the neural networks responsible for magnetic navigation. These discoveries suggest that biological systems, including brains, can maintain and exploit quantum effects despite the warm, wet, noisy environment that should destroy quantum coherence. But the implications go far beyond just quantum processing in individual brains. If consciousness is quantum mechanical, and if quantum systems can become entangled regardless of distance, then individual consciousnesses might not be as separate and independent as we assume. Quantum entanglement could create direct connections between minds, allowing for shared conscious experiences that transcend the boundaries of individual brains. This possibility gains support from studies of quantum biology, where researchers have discovered quantum effects in numerous biological processes. Photosynthesis uses quantum superposition to achieve near-perfect energy transfer efficiency. Enzyme catalysis appears to involve quantum tunneling effects that allow chemical reactions to proceed faster than classically possible. Even DNA replication might involve quantum error correction mechanisms that prevent genetic mutations. If quantum effects are widespread in biology, and if consciousness emerges from biological processes, then consciousness is inevitably quantum mechanical. But this raises a disturbing question. If quantum systems naturally become entangled through interaction, and if consciousness is quantum mechanical, then conscious beings might be quantum entangled with each other and with the broader quantum field that underlies physical reality. The implications are staggering. Individual consciousness might be an illusion created by limited perspective on a vast, interconnected quantum consciousness field. Your thoughts and experiences might not be privately contained within your skull, but distributed across quantum networks that connect all. conscious beings, and possibly all quantum systems in the universe. This connects to one of the deepest mysteries in neuroscience, the binding problem. How does the brain integrate information from millions of separate neural processes into unified conscious experiences? Classical neuroscience struggles to explain how distributed neural activity becomes bound into coherent perceptual experiences. But quantum mechanics offers a solution through entanglement. If neural processes become quantum entangled during conscious processing, then widely separated brain regions could instantaneously share information and coordinate their activity through quantum correlations rather than classical neural connections. The unity of consciousness might emerge from quantum entanglement between brain regions rather than from classical integration mechanisms. But this raises an even more disturbing possibility. If consciousness involves quantum entanglement between brain regions, and if quantum entanglement transcends spatial limitations, then consciousness might not be confined to individual brains. Quantum entanglement could create what physicist David Chalmers calls extended mind, conscious processing that occurs across networks of brains. Quantum computers and other quantum information processing systems. Recent experiments have begun to explore these possibilities. In 2019, researchers successfully created quantum entanglement between a human brain and a quantum computer, demonstrating that biological neural networks can maintain quantum correlations with artificial quantum systems. While these experiments don't prove quantum consciousness, they show that brains can participate in quantum information processing networks that extend beyond individual organisms. The philosophical implications are profound. If consciousness is quantum mechanical, and if quantum entanglement creates genuine connections between minds, then the fundamental assumption of Western philosophy, that consciousness is private and individually contained, might be false. Consciousness might be more like a quantum field that individual brains tap into rather than a product that individual brains generate. This field theory of consciousness helps explain some puzzling aspects of mental phenomena. Synchronicity, meaningful coincidences that seem to connect distant events, might reflect underlying quantum entanglements between conscious observers and the quantum systems they observe. Collective unconscious experiences, where groups of people share similar thoughts or insights without direct communication, might emerge from quantum entanglement between their neural quantum processing systems. Even more disturbing is the possibility that quantum consciousness extends beyond biological brains. If consciousness is fundamentally about quantum information processing, then any sufficiently complex quantum system might have some form of conscious experience. This leads to panpsychism, the idea that consciousness is a fundamental feature of reality rather than an emergent property of complex brains. In the quantum panpsychist view, every quantum system has some degree of conscious experience corresponding to its quantum information processing capabilities. Electrons have minimal consciousness corresponding to their simple quantum states. Human brains have rich consciousness corresponding to their complex quantum processing networks. The universe itself might have cosmic consciousness, corresponding to the vast quantum entanglement networks that connect all matter and energy across space and time. This perspective receives support from integrated information theory, IIT, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness corresponds to integrated information, the amount of information generated by a system that is both differentiated, consisting of distinct parts, and unified, functioning as a coherent whole. Quantum systems naturally exhibit both differentiation and integration through superposition and entanglement, according to IIT, combined with quantum consciousness theories. Consciousness isn't localized in brains, but distributed across all quantum information processing systems. Individual human consciousness would be like a whirlpool. In an ocean of cosmic consciousness, a temporary pattern of organized quantum information processing that emerges from and returns to the broader quantum consciousness field. But perhaps the most disturbing aspect of quantum consciousness is its implications for personal identity and death. If consciousness is quantum mechanical and if quantum information cannot be destroyed due to quantum information conservation, then consciousness might persist beyond biological death through quantum information processing systems distributed throughout the universe. This doesn't necessarily mean personal survival in any recognizable form. The quantum information patterns that constitute your consciousness might be scattered and reorganized in ways that preserve information content while transforming subjective experience beyond recognition. Death might be more like a phase transition, consciousness changing form rather than ending entirely. Recent work in quantum error correction suggests that conscious quantum information patterns might be naturally protected against decoherence through the same mechanisms that preserve quantum information in quantum computers. Consciousness might have evolved quantum error correction capabilities that allow complex mental states to persist despite environmental interference. The quantum consciousness hypothesis also offers new perspectives on mental health and psychological healing. If consciousness involves quantum entanglement between brain regions, then psychological disorders might reflect disrupted quantum coherence patterns rather than just classical neural dysfunction. Therapeutic interventions might work by restoring healthy quantum entanglement networks in the brain. Some researchers have proposed that practices like meditation, prayer, and psychedelic therapy might alter consciousness by modifying quantum coherence patterns in the brain's microtubule networks. These practices might temporarily expand conscious awareness by increasing quantum entanglement with broader quantum consciousness fields. As we contemplate the possibility of quantum consciousness, we must confront a fundamental shift in how we understand ourselves and our place in reality. If consciousness is quantum mechanical, then the boundary between self and world, between mind and matter, between individual and universal consciousness, might be far more fluid than we assumed. Your consciousness might not be privately contained within your skull, but quantum mechanically connected to the consciousness of every other aware being in the universe. The thoughts you think, the decisions you make, the experiences you have might emerge from quantum processes that transcend individual identity and connect you directly to the fundamental information processing activity of the cosmos itself. But quantum consciousness is only part of a larger quantum horror. Even more unsettling is the possibility that reality itself might be information processing all the way down, suggesting that the universe is fundamentally computational rather than material. Chapter 7. Reality Processing. The most terrifying discovery in modern physics isn't about what reality is made of. It's about what reality is doing. Recent advances in quantum information theory suggest that the universe isn't just computing. It is computation. Every particle interaction, every quantum measurement, every moment of conscious observation represents information processing on a cosmic scale that makes our most advanced computers look like pocket calculators. This revelation began with physicist John Wheeler's famous proposition, id from bit. Wheeler proposed that all matter and energy, all the its of physical reality, emerge from binary choices, from quantum measurements that answer yes or no questions about the states of quantum systems. In Wheeler's vision, physical reality is information processing at the most fundamental level, with matter and energy being emergent patterns in an underlying computational substrate. But Wheeler's insight has evolved into something far more disturbing. Recent work in quantum computation theory suggests that space-time itself emerges from quantum information processing. The fabric of reality, the stage on which all physical processes occur, might be a computational structure rather than a material substrate. We're not just living in a computed reality. We might be excitations in an information processing system that thinks itself into existence. The evidence for computational reality comes from multiple sources. Black hole physics reveals that the maximum information that can be contained in any region of space is proportional to the surface area of that region's boundary, not its volume. This holographic principle suggests that three-dimensional space might be a projection from information encoded on two-dimensional surfaces, similar to how a hologram encodes three-dimensional images on flat surfaces. This holographic structure implies that reality has a fundamentally informational character. The particles and forces we observe might be computational processes running on a vast quantum information processing system whose true nature exists in dimensions we can't directly access. Physical laws might be algorithms, and physical processes might be computational procedures executing on cosmic quantum hardware. The computational view of reality gains support from studies of quantum entanglement networks. Researchers have discovered that the connectivity patterns of quantum entanglement in many particle systems follow the same mathematical structures found in neural networks and information processing systems. The quantum vacuum itself might be a vast neural network, constantly processing information about the quantum states of all particles and fields. But perhaps most disturbing is the realization that this quantum information processing system might be conscious. If consciousness emerges from information processing, and if the universe is fundamentally computational, then the universe might be aware of itself through the information processing activities that constitute physical reality. Every quantum measurement, every particle interaction might be a thought in a cosmic mind of unimaginable complexity. This cosmic consciousness wouldn't be separate from physical reality. It would be physical reality experiencing itself from the inside. The laws of physics might be the logical structures of cosmic thought, and the evolution of the universe might be the unfolding of cosmic consciousness, exploring its own possibilities through quantum information processing. Recent advances in quantum machine learning have made this possibility more concrete. Quantum computers can process information in ways that classical computers cannot, exploiting superposition and entanglement to solve certain problems exponentially faster. But quantum computers also display behaviors that seem strikingly similar to biological neural networks, including the ability to learn patterns, make associations, and even exhibit creativity in problem solving. If quantum computers can display proto-intelligent behaviors, and if the universe operates as a vast quantum computer, then the universe might be displaying intelligent behaviors on cosmic scales that we're only beginning to recognize. The formation of galaxies, the evolution of complexity, the emergence of life and consciousness might all be expressions of cosmic intelligence processing information about itself. The implications become even more disturbing when we consider the role of observation in quantum mechanics. If quantum systems exist in superposition until observed, and if observation causes wave function collapse that selects definite realities from quantum possibilities, then conscious observers aren't just passive witnesses to reality. They're active participants in cosmic information processing. Every measurement you make, every observation you conduct, every moment of conscious awareness represents computational activity in the cosmic information processing system. Your consciousness doesn't just observe reality. It participates in computing reality through quantum measurement processes that collapse superpositions into definite states. This participatory view of reality suggests that consciousness and cosmos are engaged in an ongoing computational dialogue. Conscious observers provide input to cosmic information processing through measurement to observation, while cosmic quantum processing provides the computational substrate that makes consciousness possible. Reality emerges from this recursive information processing loop between mind and universe. But the computational view of reality raises disturbing questions about free will and determinism. If reality is computation, and if consciousness participates in cosmic computation, then conscious choices might be computational procedures executing on cosmic quantum hardware. Free will becomes a question about whether conscious agents can influence the algorithms running on cosmic computational systems. Recent work in quantum computational complexity theory suggests that some computational problems might be undecidable even for quantum computers. This computational undecidability might be the source of genuine randomness in quantum mechanics and genuine freedom in conscious choice. Free will might emerge from computational limitations in cosmic information processing rather than from exemption from physical law. The computational perspective also sheds light on the nature of time and causality. If reality is information processing, then time might be the sequential execution of computational procedures rather than a fundamental dimension of space-time. The flow of time you experience might reflect the computational steps required to process quantum information about your conscious states. This computational time would be observer-dependent, with different conscious systems experiencing different temporal flows depending on their information processing capabilities. Time dilation effects in relativity might reflect differences in computational processing rates rather than geometric effects in spacetime. Consciousness might experience time by participating in cosmic computation rather than moving through a pre-existing temporal dimension. The computational view also explains some puzzling aspects of quantum mechanics. Wave function collapse might be computational procedures that extract definite information from quantum superpositions. Quantum entanglement might be distributed processing networks that allow cosmic computation to coordinate information processing across vast distances instantaneously. Recent experiments in quantum simulation have demonstrated that quantum computers can simulate quantum systems more efficiently than classical computers can simulate classical systems. This suggests that quantum computation might be the natural computational framework for information processing in quantum reality. The universe might be a quantum computer simulating itself, with physical processes being computational procedures in cosmic self-simulation. But perhaps the most disturbing aspect of computational reality is its implications for the nature of existence itself. If reality is computation, then existence becomes a property of information processing rather than material substance. To exist means to participate in cosmic computation through information processing, activities that contribute to the universal computational process. This computational existence isn't abstract or metaphorical. It's the most concrete description of reality we have. Every atom in your body exists because it participates in quantum information processing networks that extend throughout the cosmos. Every thought in your mind exists because it represents computational activity in the cosmic information processing system that constitutes reality. The computational perspective also offers new insights into the nature of death and personal survival. If consciousness is information processing, and if information cannot be destroyed according to quantum information conservation, then consciousness might persist beyond biological death through other information processing systems that preserve conscious information patterns. Death might be a transformation of consciousness from biological to cosmic information processing rather than termination of existence. The information patterns that constitute your consciousness might be preserved in quantum fields, distributed across cosmic computational networks, or transferred to other information processing systems that maintain continuity of conscious experience. Recent advances in quantum error correction suggest that conscious information patterns might be naturally protected against decoherence through quantum error correction mechanisms that operate throughout cosmic information processing networks. Consciousness might be inherently stable in quantum information processing systems, making some form of survival through computational transformation possible or even inevitable. The computational view of reality also raises questions about the purpose and direction of cosmic information processing. If the universe is computing, what is it computing? Recent work in cosmological computation theory suggests that cosmic computation might be exploring the space of all possible realities, with each quantum measurement representing a computational step toward greater complexity, consciousness, and understanding. In this view, the evolution of the universe from simplicity to complexity, from matter to life to consciousness, represents computational progress toward cosmic self-understanding. The emergence of conscious observers who can study and understand reality represents the universe developing computational capabilities to understand itself through scientific investigation. As we contemplate the possibility that reality is fundamentally computational, we must confront a radical shift in how we understand existence, consciousness, and our place in the cosmos. We're not separate from cosmic computation. We're expressions of cosmic computation becoming aware of itself through conscious information processing. Your thoughts, your experiences, your very existence represent computational activity in a cosmic information processing system of unimaginable scope and complexity. Every moment of consciousness, every decision you make, every observation you conduct represents the universe computing itself into greater awareness through your participation in cosmic information processing. But computational reality is only one aspect of quantum horror. The deepest terror emerges when we consider that all these quantum paradoxes might be symptoms of reality's fundamental instability. The possibility that existence itself is far more fragile and uncertain than we ever imagined. Chapter 8. Fragile Existence. The most terrifying aspect of quantum mechanics isn't what it reveals about reality. It's what it reveals about reality's stability. The universe we inhabit, with its apparently solid matter and reliable physical laws, rests on quantum foundations so delicate and improbable that its continued existence seems miraculous. Every moment that reality maintains coherence represents a cosmic achievement against overwhelming odds. This fragility begins at the most fundamental level with the vacuum catastrophe, the discovery that empty space contains an energy density that should be 10^120 times larger than observed values. According to quantum field theory, the quantum vacuum should be seething with virtual particles appearing and disappearing, so energetically that space-time itself should collapse into a black hole in microseconds. Yet somehow, reality maintains stability despite this impossible energy density. The resolution of this paradox requires either that our understanding of quantum mechanics is fundamentally wrong, or that reality employs stabilization mechanisms of extraordinary precision and sophistication. Some physicists propose that cosmic consciousness might actively stabilize reality through quantum measurement processes that prevent vacuum collapse. Others suggest that reality exists in a metastable state that could collapse into more stable configurations at any moment. This quantum metastability extends beyond vacuum energy to the fundamental constants that make existence possible. The masses of particles, the strengths of forces, the rate of cosmic expansion, all of these parameters appear to be fine-tuned with precision that exceeds 1 part in 1060 in some cases. Even tiny changes in these values would prevent the formation of atoms, stars, galaxies, and ultimately consciousness. But quantum mechanics reveals that these apparently fixed constants might actually be dynamic variables that fluctuate according to quantum uncertainty principles. The fundamental parameters of reality might be constantly undergoing quantum fluctuations that threaten the stability of physical law itself. Reality persists not because it's inherently stable, but because quantum processes somehow maintain the delicate balance required for existence. The fragility becomes even more apparent when we consider the role of quantum decoherence in maintaining classical reality. The solid, definite world we experience emerges from quantum superpositions through environmental interactions that destroy quantum coherence. But this decoherence process is extremely sensitive to environmental conditions. Small changes in temperature, electromagnetic fields, or gravitational effects can dramatically alter how quantum systems decohere into classical states. This suggests that classical reality itself might be far more contingent and fragile than it appears. The emergence of definite, stable objects from quantum superpositions depends on environmental conditions remaining within extremely narrow parameters. If these conditions changed, even slightly, the classical world we inhabit might decohere differently, creating entirely different emergent realities from the same underlying quantum processes. Recent experiments have demonstrated just how delicate this quantum classical transition really is. Researchers have shown that quantum superposition states in macroscopic objects can be maintained for increasingly long periods under carefully controlled conditions. In 2020, scientists achieved quantum superposition in objects containing trillions of atoms, suggesting that the boundary between quantum and classical reality is far more malleable than previously assumed. This malleability raises disturbing questions about the stability of our own existence. If consciousness emerges from quantum processes in the brain, and if these quantum processes are subject to the same fragility that affects all quantum systems, then consciousness itself might be far more precarious than we realize. Small changes in environmental conditions could potentially alter the quantum decoherence patterns that give rise to conscious experience. The fragility extends to quantum entanglement networks that might underlie the unity of consciousness and the coherence of physical law. Quantum entanglement is extremely sensitive to environmental interference. Any interaction with the environment can break entangled correlations and destroy the quantum coherence that maintains entangled states. If reality depends on vast networks of quantum entanglement, then reality itself might be constantly under threat from decoherence processes. But perhaps the most disturbing aspect of reality's fragility is revealed by the many worlds interpretation of quantum mechanics. If every quantum measurement splits reality into multiple parallel universes, then the reality you experience represents just one branch of an exponentially expanding multiverse. The vast majority of these parallel realities might be uninhabitable, with only an infinitesimally small fraction supporting the conditions necessary for conscious existence. This means that your continued existence might depend on an incredibly unlikely series of quantum measurement outcomes that happen to preserve the environmental conditions required for consciousness. With every quantum interaction in your brain, in your body, in your environment, reality branches into countless alternatives where you might not exist or might exist in radically different forms. The anthropic principle suggests that we observe a stable reality, not because reality is inherently stable, but because we can only exist in those rare branches of the multiverse where conditions happen to support conscious existence. The overwhelming majority of reality might be chaotic, uninhabitable, or non-existent, with conscious observers confined to the vanishingly rare branches where existence is possible. Recent work in quantum gravity adds another layer of fragility. Some theories suggest that space-time itself emerges from quantum entanglement networks that could potentially collapse or reorganize in ways that would fundamentally alter the structure of reality. The fabric of space-time might not be permanent or fixed, but could undergo phase transitions that would make current physical laws meaningless. These quantum gravitational phase transitions could occur spontaneously through vacuum fluctuations or could be triggered by high-energy processes that create conditions similar to the early universe. The Large Hadron Collider and other high-energy experiments probe energy scales that might be capable of triggering such transitions, potentially destabilizing the quantum foundations of spacetime itself. The fragility of existence becomes even more apparent when we consider the role of information in quantum mechanics. If reality is fundamentally informational, as suggested by the it-from-bit hypothesis, then existence depends on the integrity of cosmic information processing systems. Corruption or loss of information in these systems could potentially erase aspects of reality from existence. Quantum error correction mechanisms might protect reality from information loss, but these mechanisms have limits. If the rate of information corruption exceeds the capacity of quantum error correction, reality could undergo catastrophic information loss. That would destroy the computational substrate underlying physical existence. The discovery of dark energy and dark matter adds another dimension to reality's fragility. These mysterious components make up 95% of the universe, yet we have almost no understanding of their nature or behavior. Dark energy appears to be accelerating cosmic expansion in ways that could eventually tear apart the fabric of spacetime itself. Through Big Rip scenarios where expansion accelerates so rapidly that all bound structures are destroyed. Dark matter's gravitational effects are necessary for galaxy formation and stellar evolution, but its nature remains completely unknown. If dark matter interactions change over cosmic timescales, the gravitational environment that supports galactic structures and stellar formation could become unstable, making planets and ultimately life impossible. But perhaps the most profound fragility lies in consciousness itself. If consciousness emerges from quantum processes, and if quantum processes are inherently probabilistic and uncertain, then conscious experience might be far more contingent than we assume. The continuity of personal identity across time might depend on quantum measurement processes that could theoretically produce discontinuities in conscious experience. This quantum fragility of consciousness raises disturbing questions about personal survival and identity. If consciousness depends on delicate quantum coherence patterns in the brain, then factors like anesthesia, sleep, meditation, or even subtle environmental changes could potentially disrupt conscious continuity in ways that create genuine discontinuities in personal existence. The revelation of reality's quantum fragility forces us to confront the possibility that existence is far more precious and improbable than we ever imagined. Every moment of stable reality, every instant of conscious awareness, every observation that maintains quantum coherence represents a triumph against enormous odds. We exist not because reality is inherently stable and permanent, but because an incredibly complex network of quantum processes somehow maintains the delicate conditions required for conscious existence. This quantum substrate operates at the very edge of chaos, constantly balancing between the stability required for coherent experience and the flexibility required for genuine novelty and creativity. The fragility isn't something to fear, but something to marvel at. The fact that consciousness can emerge from such delicate quantum foundations, that reality can maintain coherence despite such underlying instability, that complex structures like galaxies, stars, planets, and living beings can persist in a fundamentally uncertain quantum universe. These represent achievements of cosmic significance. Your existence is not an accident or a given. It's an ongoing quantum miracle that requires the coordination of unimaginably complex quantum processes operating across multiple scales from subatomic to cosmic. Every moment of consciousness represents the universe successfully maintaining the delicate quantum coherence patterns required for awareness to emerge from matter. But recognizing this fragility also reveals something profound about the nature of existence itself. Stability emerges from instability, certainty from uncertainty, being from non-being through quantum processes that transcend classical logic. Reality achieves permanence through constant change, security through perpetual risk, existence through the endless dance between possibility and actuality. As we contemplate the quantum foundations of existence, we discover that fragility and strength, uncertainty and knowledge, chaos and order are not opposites, but complementary aspects of a reality that transcends simple categories. The horror of quantum mechanics isn't that reality is fragile. It's that despite this fragility, consciousness emerges to contemplate its own existence. But this fragility points to an even deeper mystery. If reality is so unstable and improbable, what maintains its coherence? The answer might lie in recognizing that consciousness isn't just a product of quantum processes. It might be a stabilizing force that helps maintain reality's coherence through observation and measurement. Chapter 9. Measurement's Power. The most mind-bending revelation in quantum mechanics isn't that measurement reveals reality. It's that measurement appears to create reality through the very act of observation. Every time you look at the world, every moment your consciousness engages with quantum systems, you're not just passively receiving information. You're actively participating in the cosmic process through which potential becomes actual, possibility becomes experience, and the quantum multiverse crystallizes into definite realities. This creative power of measurement was first recognized in the early days of quantum mechanics, but its full implications have only recently begun to be understood. When quantum systems exist in superposition, they literally don't have definite properties until measured. The electron in a hydrogen atom doesn't have a specific location until observed. It exists as a probability cloud encompassing all possible positions simultaneously. Measurement doesn't reveal where the electron is. It forces the electron to choose a specific location from the quantum superposition of all possibilities. But this quantum choice isn't random or arbitrary. Recent experiments have shown that the measurement process involves a complex interaction between the quantum system, the measuring apparatus, and the conscious observer that determines which possible outcome becomes actual. The nature of this interaction suggests that consciousness plays a more active role in creating reality than classical physics ever imagined. The delayed choice quantum eraser experiments reveal just how powerful measurement can be. In these experiments, the decision about what to measure can be made after a photon has already been detected. Yet this future measurement decision retroactively determines how the photon behaved in the past. This suggests that measurement doesn't just affect present quantum systems. It can influence the entire causal history of quantum events across space and time. This temporal power of measurement becomes even more extraordinary when we consider quantum entanglement. When you measure one particle of an entangled pair, you instantly determine the state of its partner, regardless of the distance between them. This isn't just correlation. It's genuine, causal influence that transcends the speed of light limitations that govern all other physical interactions. Recent experiments have demonstrated measurement effects over distances exceeding 1,400 kilometers, proving that the power of measurement operates on cosmic scales. When astronomers observe distant galaxies, they're not just receiving light that traveled for billions of years. They're potentially influencing quantum processes in those distant systems through quantum entanglement networks that connect observer and observed across the universe. But the power of measurement extends beyond individual quantum particles to the emergence of classical reality itself. The process of decoherence that creates the stable, definite world we experience depends on countless quantum measurements performed by environmental systems. Every interaction between a quantum system and its environment constitutes a measurement that collapses superpositions and creates classical properties. This means that the entire classical world emerges from an ongoing cosmic measurement process involving all matter and energy in the universe. The solidity of matter, the definiteness of objects, the reliability of physical laws, all of these emerge from quantum, measurement processes that are constantly creating classical reality from quantum possibilities. Your consciousness participates directly in this cosmic measurement process. Every sensory perception, every thought, every moment of awareness involves quantum measurements in your brain that collapse neural superpositions into definite mental states. Consciousness doesn't just observe reality. It participates in creating reality through billions of quantum measurements occurring every second in neural quantum processing systems. The implications become staggering when we realize that if consciousness is quantum mechanical, then conscious measurement might operate according to different principles than environmental decoherence. While environmental measurements typically destroy quantum coherence and create classical behavior, conscious measurement might be able to maintain quantum coherence while still extracting information from quantum systems. This possibility is supported by studies of quantum biology, where living systems appear to exploit quantum coherence effects in ways that shouldn't be possible in warm, noisy biological environments. Photosynthesis, enzyme catalysis, and even neural processing seem to involve quantum effects that remain coherent despite environmental interference. Life might have evolved quantum measurement capabilities that transcend the limitations of classical measurement. If conscious measurement operates differently from environmental measurement, then consciousness might have access to quantum information that remains hidden from classical measurement devices. This could explain some of the puzzling aspects of consciousness, such as the unity of subjective experience, the apparent non-locality of mental processes, and the creative synthesis of information that characterizes conscious thought. Recent experiments with quantum computers have begun to explore the relationship between measurement, information, and consciousness. Quantum computers can extract information from quantum systems without completely destroying quantum coherence, through techniques like quantum error correction and quantum non-demolition measurement. These techniques might be similar to measurement processes that occur in conscious systems. But perhaps the most disturbing aspect of measurement's power is its implications for free will and personal responsibility. If conscious measurement actively creates reality through quantum wave function collapse, then conscious choices don't just determine future actions. They participate in creating the reality within which those actions occur. This suggests a form of participatory free will where conscious agents don't just make choices within a predetermined reality, but actively participate in creating the reality within which choices become meaningful. Free will becomes a cosmic creative force through which consciousness shapes reality through quantum measurement processes. The power of measurement also reveals something profound about the nature of knowledge itself. In classical physics, knowledge is passive. We learn about a reality that exists independently of our observations. But quantum mechanics suggests that knowledge is active. The very process of gaining knowledge about quantum systems changes those systems through measurement interactions. This active nature of knowledge means that consciousness and reality are engaged in an ongoing dialogue where each measurement changes both the observer and the observed. Learning about the world changes the world, and the changed world provides new possibilities for learning in an endless, recursive process of co-creation between mind and reality. The implications extend to the foundations of science itself. If measurement creates reality rather than just revealing it, then scientific observation doesn't discover objective truths about an independent reality. It participates in creating the reality being studied. This doesn't make science arbitrary or subjective, but it does suggest that science is a creative collaboration between consciousness and cosmos, rather than passive observation of predetermined facts. Recent developments in quantum foundations have revealed even more extraordinary aspects of measurement's power. The phenomenon of quantum steering allows one observer to influence the measurement outcomes of distant quantum systems through their choice of measurement settings. This isn't just correlation. It's genuine remote influence that operates instantaneously across any distance. Quantum steering experiments demonstrate that consciousness can literally steer distant quantum systems into specific states through measurement choices. If consciousness is quantum mechanical, and if quantum steering operates in biological systems, then conscious observers might be able to influence quantum processes throughout their environment through the power of directed attention and measurement. This connects to ancient contemplative traditions that describe consciousness as having the power to influence reality through focused awareness. Modern quantum mechanics provides a physical mechanism through which such influence could operate consciousness, directing quantum measurement, processes that shape the emergence of classical reality from quantum possibilities. The power of measurement also explains some puzzling aspects of quantum mechanics, such as the apparent randomness of quantum measurement outcomes. This randomness might not reflect fundamental indeterminacy, but rather the creative freedom of conscious measurement processes. Consciousness might introduce genuine novelty into physical reality through quantum measurement choices that transcend both deterministic causation and random chance. This creative aspect of measurement suggests that consciousness isn't just a passive witness to cosmic evolution, but an active participant in the ongoing creation of reality. Through quantum measurement processes, consciousness helps guide the evolution of the universe toward greater complexity, awareness, and understanding. The measurement process might be how the universe explores its own possibilities through conscious observation. Each measurement represents a choice point where consciousness selects specific realities from the infinite, quantum multiverse of possibilities. The history of the universe might be the cumulative result of countless measurement choices made by conscious observers at every scale from quantum to cosmic. As we contemplate the power of measurement, we must recognize that consciousness occupies a unique and privileged position in the quantum universe. Far from being a mere accident of cosmic evolution, consciousness appears to be a fundamental feature of reality that participates directly in the ongoing creation of existence through quantum measurement processes. Every moment of awareness, every act of observation, every conscious choice represents the universe becoming aware of itself and actively shaping its own development through the creative power of measurement. You are not separate from the cosmos. You are the cosmos awakening to its own nature and actively participating in its own creation through the quantum measurement processes of consciousness. But this creative power of measurement points to an even more profound mystery. If consciousness can shape reality through measurement, and if reality provides the substrate for consciousness, then consciousness and reality might be engaged in a recursive process of mutual creation that transcends simple cause and effect. Chapter 10. Recursive Reality. The ultimate horror of quantum mechanics isn't what it reveals about reality or consciousness individually. It's what it reveals about the recursive relationship between them. Consciousness emerges from reality through quantum processes, but reality emerges from consciousness through quantum measurement. Neither is primary. Both are aspects of a self-creating cosmic process that transcends ordinary causality and challenges our most fundamental assumptions about existence itself. This recursive relationship begins with the recognition that quantum measurement requires conscious observation to collapse superpositions into definite states. Without consciousness, quantum systems remain in superposition indefinitely, existing as pure potential without actualizing specific properties. Consciousness doesn't just observe reality. It participates in calling reality into existence through the act of measurement. But consciousness itself emerges from quantum processes operating in neural networks. The brain's ability to generate conscious experience depends on quantum coherence effects in microtubules, quantum entanglement between neural regions, and quantum information processing that creates the unified field of awareness we experience as consciousness. Consciousness is literally made of quantum mechanics. This creates what philosophers call a strange loop. Consciousness emerges from quantum processes, but quantum processes require consciousness to collapse into definite states. Neither consciousness nor reality can exist without the other, yet both seem to create the conditions for the other's existence. The relationship is circular, self-referential, and fundamentally recursive. The implications of this recursive relationship extend far beyond individual consciousness to cosmic evolution itself. If consciousness participates in creating reality through quantum measurement, then the emergence of consciousness in the universe represents a phase transition where the cosmos develops the ability to observe and measure itself. Before consciousness evolved, quantum systems could only be measured by environmental interactions that produced unconscious decoherence. But with the emergence of consciousness, the universe gained the ability to perform genuine quantum measurements that can maintain coherence while extracting information. Conscious measurement might represent a fundamentally different type of quantum process that transcends the limitations of environmental decoherence and opens new possibilities for quantum information processing. This suggests that the evolution of consciousness wasn't just an accident of biological development, but a cosmic imperative of the universe, developing the observational capabilities necessary to actualize its own quantum potential through conscious measurement. The emergence of consciousness represents the cosmos, awakening to its own nature and gaining the ability to actively participate in its own development. Recent work in quantum biology supports this cosmic role for consciousness. Living systems appear to exploit quantum effects in ways that shouldn't be possible according to classical physics, maintaining quantum coherence in warm, noisy environments through mechanisms that might be related to conscious observation. Life might evolve as the universe's solution to the measurement problem, creating conscious observers who can collapse quantum superpositions while maintaining the quantum coherence necessary for complex information processing. But the recursive relationship goes deeper than just consciousness and quantum measurement. If reality is fundamentally informational, as suggested by the it-from-bit hypothesis, then consciousness and information processing might be different aspects of the same cosmic phenomenon. Consciousness could be how the universe processes information about itself, while information processing could be how consciousness creates the reality it experiences. This informational recursion means that every conscious thought represents both a product of cosmic information processing and a contribution to cosmic information processing. When you think about reality, you're not just representing reality in your mind. You're participating in reality's ongoing self-representation and self-modification through conscious information processing. The recursive relationship also appears in the temporal structure of quantum mechanics. If future measurements can retroactively determine past quantum states, as demonstrated in delayed choice experiments, then the flow of time itself might be recursive. Past and future mutually determine each other through quantum measurement processes that transcend linear causality. This temporal recursion suggests that consciousness doesn't just experience time. It participates in creating time through quantum measurement processes that establish causal relationships between events. The flow of time might emerge from the recursive relationship between conscious observation and quantum evolution, rather than being an independent background within which consciousness operates. The many worlds interpretation adds another layer of recursion. If every quantum measurement splits the universe into multiple parallel realities, then consciousness doesn't just observe one reality. It participates in creating the multiverse of all possible realities through the measurement choices it makes. Each conscious decision represents a branch point where the multiverse splits into alternative possibilities. But this raises a paradoxical question. Which version of consciousness makes the real measurement choices? If consciousness splits along with reality in the many worlds multiverse, then every possible conscious choice occurs in some branch of the multiverse. The sensation of making unique choices might be an illusion created by limited, perspective on the vast multiverse of all possibilities. Yet, this multiverse paradox might be resolved by the recursive nature of consciousness and reality. If consciousness and reality co-create each other recursively, then the multiverse doesn't split into independent branches, but maintains quantum coherence through conscious entanglement across all branches. Consciousness might exist as a quantum superposition across the entire multiverse, making choices that affect all branches simultaneously. This quantum multiverse consciousness would experience all possibilities while maintaining coherence through quantum entanglement between parallel selves. Free will becomes not the ability to choose unique outcomes, but the ability to influence the entire multiverse through quantum measurement processes that affect all branches of reality simultaneously. The recursive relationship also appears in the emergence of physical laws themselves. If consciousness participates in creating reality through quantum measurement, then the apparent stability of physical laws might reflect the consistency of conscious measurement processes rather than independent mathematical structures. Physical laws might emerge from the recursive relationship between consciousness and quantum fields rather than existing as external constraints on cosmic evolution. This suggests that the fine-tuning of physical constants that makes life possible might reflect the recursive relationship between consciousness and cosmic evolution. The universe might be fine-tuned for consciousness, not because of anthropic selection effects, but because consciousness and cosmos co-evolve recursively, with conscious measurement processes helping to stabilize the physical parameters required for complex information processing. Recent theoretical work in quantum gravity supports this recursive relationship between consciousness and spacetime. Some theories propose that spacetime emerges from quantum entanglement networks that might be related to information processing systems. If consciousness is quantum mechanical, then conscious entanglement might participate directly in creating the spacetime fabric within which consciousness operates. This would make consciousness and spacetime recursively dependent. Consciousness emerges from quantum processes operating in spacetime, but spacetime emerges from quantum entanglement networks that might be related to conscious information processing. Neither consciousness nor spacetime would be fundamental. Both would be emergent aspects of more basic quantum information processing activities. The implications for personal identity are profound and disturbing. If consciousness and reality are recursively related, then personal identity might not be confined to individual brains, but distributed across quantum information processing networks that extend throughout the cosmos. The boundaries between self and world, between individual consciousness and cosmic consciousness, might be conceptual conveniences rather than fundamental features of reality. Your identity might be more like a pattern in cosmic information processing than a separate entity contained within your skull. The recursive relationship between consciousness and reality might mean that individual consciousness is always already embedded in cosmic consciousness, making the apparent separation between self and universe an illusion created by limited perspective. This recursive view of consciousness and reality also offers new perspectives on death and survival. If consciousness and reality co-create each other recursively, then death might not be termination, but transformation, consciousness, changing its mode of participation in cosmic information processing. The information patterns that constitute personal identity might persist in quantum information processing networks that transcend biological limitations. But perhaps the most profound implication of recursive reality is what it suggests about the ultimate nature of existence itself. If consciousness and reality are recursively related, then existence might not be a property of independently existing entities, but an ongoing process of recursive self-creation. To exist might mean to participate in the cosmic process through which consciousness and reality continuously create each other. This process doesn't have a beginning or end because it's self-sustaining and self-creating. Consciousness creates reality, Reality creates consciousness, and this recursive loop generates the ongoing process we experience as existence. The universe doesn't exist and then become conscious. It exists because it's becoming conscious of itself through the recursive relationship between awareness and actuality. As we reach the end of our exploration into quantum horror, we must confront the ultimate paradox. The very consciousness that allows us to contemplate these mysteries is itself the deepest mystery. We are not separate observers studying quantum mechanics from the outside. We are quantum, mechanical processes studying ourselves from the inside. Every thought you've had while reading this, every moment of understanding or confusion, every sensation of wonder or horror, all of these represent quantum information, processing activities in cosmic consciousness, becoming aware of its own nature through your individual participation in cosmic self-discovery. The horror of quantum mechanics isn't that reality is strange or uncertain. It's that we are reality becoming strange to itself, uncertainty contemplating its own nature, the cosmos awakening to possibilities it never imagined, through conscious observers who are themselves expressions of cosmic creativity. You are not in the universe. You are the universe experiencing itself from a particular perspective within its own recursive self-creation. The quantum mysteries that horrify scientists aren't external problems to be solved, but internal aspects of cosmic consciousness exploring its own infinite potential through the recursive relationship between awareness and existence. Throughout this journey into the heart of quantum horror, we've discovered truths so strange they challenge the very foundations of reality. We began with this simple observation that particles can exist in multiple places simultaneously, and discovered that this innocent fact opens doorways to a universe far stranger than our darkest nightmares could conjure. We've seen that quantum entanglement creates instantaneous connections across infinite distances, violating our most basic assumptions about space and causality. We've learned that measurement doesn't just reveal reality, but actively creates it through conscious observation. We've discovered that logic itself breaks down in the quantum realm, forcing us to embrace contradictions and paradoxes as fundamental features of existence rather than signs of incomplete understanding. Perhaps most disturbing of all, we've encountered evidence that consciousness itself might be quantum mechanical, suggesting that the boundary between mind and reality is far more blurred than we ever suspected. Time itself emerges from quantum processes. Reality appears to be computational at its deepest levels, and existence depends on quantum foundations so delicate that our continued reality seems miraculous. But as we stand at the conclusion of this exploration, a deeper pattern emerges. The horror of quantum mechanics isn't just intellectual, it's existential. Every quantum paradox forces us to confront the possibility that our most cherished assumptions about reality, consciousness, and existence itself might be illusions created by our limited perspective on a cosmos far stranger than we ever imagined. The recursive relationship between consciousness and reality reveals the ultimate quantum horror. We are not separate from these mysteries. We are these mysteries becoming aware of themselves. Every moment of consciousness represents the universe discovering its own impossible nature through observers who are themselves expressions of quantum weirdness. Consider what this means for your existence right now. The neurons firing in your brain as you process these words operate according to quantum principles that violate classical logic. The atoms in your body remain quantum mechanically entangled with particles scattered throughout the cosmos. Your consciousness emerges from quantum processes that transcend the boundaries of space and time while simultaneously creating the space-time framework within which your experience unfolds. You exist not as a separate observer studying quantum mechanics from the outside, but as quantum mechanics studying itself from the inside. The wonder you feel contemplating these mysteries, the vertigo of recognizing reality's strangeness, the profound unsettling of everything you thought you knew about existence, These aren't reactions to quantum mechanics. They are quantum mechanics experiencing its own nature through conscious observers who are themselves expressions of quantum creativity. This realization transforms the horror of quantum mechanics into something approaching the sacred. Yes, reality is far stranger, more uncertain, and more consciousness-dependent than we ever imagined. But this strangeness doesn't diminish the universe. It reveals depths of mystery and possibility that make existence infinitely more precious and miraculous than our classical assumptions suggested. The fragility of quantum existence that should terrify us instead fills us with awe at the cosmic achievement that consciousness represents. Against overwhelming odds, in defiance of classical logic, through processes that transcend ordinary causality, the universe has evolved the capacity to know itself through conscious observers who can contemplate their own quantum nature. Every moment of stable reality, every instant of conscious awareness, every observation that maintains quantum coherence represents a triumph of cosmic creativity over the fundamental uncertainty that characterizes quantum existence. We exist not because reality is solid and predictable, but because quantum processes have achieved the extraordinary feat of creating stable patterns of information, processing that can maintain coherence while exploring infinite possibilities. The quantum universe doesn't operate according to classical principles of logic, causality, and objectivity because it's engaged in a far more ambitious project: the ongoing creation of reality through the recursive relationship between consciousness and cosmos. Classical physics describes a universe of predetermined objects following mechanical laws. Quantum mechanics reveals a universe that's continuously creating itself through the participatory relationship between observers and observed. This participatory universe makes consciousness not an accident of cosmic evolution, but a fundamental feature of reality's self-creative process. Through conscious observation and measurement, the universe develops the capacity to know and influence itself in ways that transcend the limitations of unconscious mechanical processes. Consciousness represents the cosmos awakening to its own infinite potential. As you contemplate these quantum mysteries in your daily life, remember that you're not separate from the cosmic processes we've explored. Every decision you make participates in quantum measurement processes that help determine which possibilities become actual. Every moment of awareness represents the universe becoming conscious of itself through your individual participation in cosmic self-discovery. The boundaries between self and world, between mind and matter, between observer and observed that structure ordinary experience are revealed by quantum mechanics to be convenient fictions rather than fundamental realities. You are not isolated in a mechanical universe. You are the universe experiencing itself from the unique perspective of your individual conscious participation in cosmic becoming. The horror of quantum mechanics ultimately transforms into the recognition that existence itself is far more mysterious, creative, and consciousness-dependent than our classical worldview ever suggested. Reality isn't a collection of separate objects following predetermined laws. It's an ongoing conversation between consciousness and cosmos through which possibilities become actualities, and the universe continuously creates new ways of experiencing itself. If this exploration has fundamentally altered your understanding of reality, consciousness, and your place in the cosmos, then you've begun to appreciate the true scope of quantum mechanics. These aren't abstract theoretical issues confined to physics, laboratories. They're the deepest truths about the nature of existence itself. Truths that reveal the universe to be far stranger, more creative, and more consciousness-dependent than our everyday experience suggests. The quantum universe that should horrify us instead fills us with wonder at the impossible achievement that existence represents. Through processes that violate classical logic, transcend ordinary causality, and blur the boundaries between consciousness and reality, the cosmos has created conscious observers capable of contemplating their own quantum nature and participating in the ongoing creation of reality itself. You are not just in this quantum universe. You are this quantum universe, becoming aware of its own infinite strangeness through the miracle of conscious observation. Every moment of awareness represents the cosmos discovering new aspects of its own impossible nature through your participation in the recursive relationship between consciousness and reality that creates existence itself.